Please help me to welcome Dima Amso.
All right. Can you guys hear me? All right. It's going to take me 1 second to bring this up. Okay, great. Let's see if this comes up. Brilliant. Thanks so much for giving me the opportunity to speak to this group about infant development and infant research. I'm actually going to start with my acknowledgement slide, in case I don't get there, but I think I will. Special thanks to especially the participants and families, the funding agencies, the collaborators, and today I'm especially going to highlight the work of my postdoc, Julie Marquand, and Sarah Haas, who was in my lab and is now a graduate student at the University of Maryland. All right, so let me start by making the point that infant visual attention, in my view, is a foundational building block mechanism. Classic literature has linked infant visual attention to later cognitive function, to preschool social cognition, to adolescent intelligence, to outcomes in children born prematurely, to adult IQ, to clinical outcomes and language development in typical and atypical populations, and also most recently to diagnoses of autism. So one way to think about what's going on with respect to visual attention is that infant visual attention orienting very early on in postnatal life, one is kind of what babies are doing. So if you think about infants in the first 6 months, 8 months, a lot of what they're doing is actually just kind of sitting around drooling and looking around at the world. Yet by the end of the first postnatal year, they're brilliant, right? They've got language, they understand social cognition, they understand differences in facial emotion expressions. Something really profound is happening in that first postnatal year that sort of never repeats in its magnitude again. And I really feel like there are so many interesting ways to study what exactly the mechanisms are that are supporting that and that are continuing to support developmental cascades and trajectories subsequently. So one way to think about visual orienting is that it's playing these interesting roles in human development by biasing incoming information into the system for subsequent processing beginning very early in postnatal life. So what I'm going to show you here is just an example of what I'm talking about. This is a natural visual search. This is the child is wearing actually an eye tracker while they're sitting around playing with an experimenter. And even in a constrained setup like this, there's a lot of clutter and a lot of things are happening that they can either encode or not encode, right? A lot of what they're looking at is determining what they see, which is really starting to shape cognitive architectures at the content domain and neural architectures for that reason. So we spend a lot of time trying to think about how to study attention in infancy. And in the next few minutes, my goal is to tell you about how we study visual attention orienting through the lens of visual search, how we use visual search as a way to understand what's going on developmentally with respect to how infants are gathering information very early on in an effort to shape their learning. So I'm going to spend a few minutes talking about right at the beginning what we know about visual search just as a process, and then I'm going to break down for you 2 developing mechanisms involved in that sequence of eye movements, that is the visual search process. And those are bottom-up guidance of orienting at the level of the visual system and its interactions with posterior parietal, and also at the level of inhibition of return, which I'll explain in just a minute. Throughout, I'd ask that you keep in mind the premise that it's important to lay the developmental groundwork for both mechanisms separately if we're going to get a handle on how they might impact developmental trajectories beyond infancy. Okay? So, my lab spent a lot of years trying to understand this visual search process in nonverbal infants through the development of appropriate tasks combined with eye tracking methodology. So I'm going to show you here an example of a visual search study. So this is what the baby is, keep pressing the wrong button. This is what the baby is seeing on the screen. This is the infant's eye movements. This is their eye track, okay? The search task here is appropriate for these 3-month-olds. It's an array of red bars with a single target varying along either the motion dimension, which pops out to them, or the orientation dimension, which is substantially more effortful for them. And we actually vary target distractor similarity along both of these dimensions to try to get a sense of both their reaction times as a function of these differences, as well as the accuracies in identifying that target as a function of these differences. So So that crosshair is always, in all my videos where you see it, where those babies are looking on the screen, okay? The pattern of results is much like what you might expect in a search task in older groups. There's high accuracy and fast detection for the pop-out search. There's slower accuracy, there's slower reaction time and poorer accuracy for the more effortful search. The point of this, and I want to sort of make this point, is that by 3 months of age, the visual search tasks that we're using are capable of identifying the processes that we're comfortable with in the visual attention literature in a very predictable way. So we've more recently replicated these data in infants 3 to 9 months of age on a variant of this task, and again found this pop-out effortful search distinction, with the pop-out search is up here in gray, and the more effortful search has poorer accuracy here in black. I'm showing you each infant's data, so you can see the variability inherent in doing infant work, but still the strong pattern of developmental change over the first postnatal year. So this is 2 months and this is 10 months. And there's a large improvement in search performance between these 2 and 10 months of age, with age correlating with both pop-out and visual search. That's more effortful. I want to restate that these types of individual differences correlate with information gathering across a variety of different studies for both object perception, for facial emotion discrimination, for selection of social stimuli in video. So we've done this in a variety of different ways, and I think the pattern of results is that as visual search is developing, where infants look is determining what they see. So it's not that it's just developing and it's interesting to think about it as a mechanism, it's that it's having these functional consequences for what they're learning from the displays that we show them, and we can relate this within an infant and across infants in these types of tasks. We thought a little bit about the cortical mechanisms involved in this visual search development, and actually we've done this predominantly through computational modeling. This is the work of Matt Schlesinger, who's done a lot of wonderful work with infant data that we've collected for visual search tasks and more naturalistic object perception search tasks. And he's identified 3 parameters of interest in these models. The first is meant to represent the size of horizontal connections in visual cortex. In V1, these connections are thought to play an important role in the perception of contours that span multiple receptive fields, and also to provide a neural mechanism through which stimuli at different locations in the visual field compete for attention in a center surround sort of way. He's looked at an analog of the duration of recurrent posterior parietal activity. I think I don't know what button I press, so if I press all the buttons in there, let's see. There we go. And also, anytime you use eye movements in infancy to index anything, you have to consider the degree of oculomotor noise that's involved, because it plays a really critical role in the development of motor skills, and therefore is going to play a pretty critical role when you're using that oculomotor system as a metric. So the idea is that you can choose the range of values to simulate the development of growth of the corresponding neural substrate during infancy to try to fit the model to the developmental change that we see in the infant visual data. And the simulations have repeatedly showed that as 2 of the 3 parameters were increased, the model reproduced the visual search performance of infants. So the tuning of the 3rd parameter, this oculomotor noise variable, was not causal with respect to getting the model to fit the infant data, suggesting that there is occipitoparietal change, at least from a computational perspective, that's consistent with this visual search development. So this is the part where I hope that I can be a little bit more mechanistic about what's happening. So far I've reviewed for you the idea that visual search is available as early as 3 months, that it's important for online learning and information gathering, and that at least with computational evidence, we think that the same occipitoparietal networks that are involved in attention orienting in older populations are important behavioral changes in visual search skills that we've seen so far. So visual search is not a unitary process. It's something that we can measure, it's something that's indexing orienting behaviors, but it's not itself a mechanism. Understanding, however, the precise mechanisms underlying the development of visual search, I think, in development is critical in the long term to understanding individual differences in the derivative outcomes that I showed you a few minutes ago. So, working in the service of this goal, my lab has studied 2 critical component processes, both hinted at by the model, that I just showed you, and also thought to play a pretty critical role in the sequencing of eye movements during visual search for information gathering. I'm going to tell you a little bit about what we know so far about each. The first is bottom-up guidance for orienting, which I'll explain in just a minute. The idea is that this process gets infants to a location in space. The second is its inhibition of return mechanism, which is thought to play a critical role in visual search by suppressing previously attended locations, whether overtly or covertly, so that search is efficient, so that you don't continually perseverate and return to a location that's been attended, either because it wasn't useful or because you've already learned the information there. So I'm going to make the argument today that in doing that, in suppressing that previously attended location and its contents, what's happening in visual search is that this inhibition of return mechanism is really creating a more robust signal at the attended location. It's basically suppressing the interference from the previous eye movement, therefore supporting, it's this way that attention modulates visual cortex, striate and extrastriate activity. And I'll show you some evidence of that, therefore supporting encoding at the attended location. So now we've linked visual search and attentional orienting in infancy not just to getting to a location in space, but perhaps to the depth of encoding, to the memory formation at that location. But first, let me tell you a little bit about what we know about bottom-up guidance. I'm showing you an example in the center here of visual salience maps. So these are computationally derived, and they represent the amount of visual information in the environment. So these are not about they're not representing what people see. They're taking a snapshot, a frame of what's happening in the world during an orienting process. And these are computational models of where the most visually salient regions are in those displays. They're basically a linear summation of all the different visual channels at the level of occipital processing. So color, motion, orientation, etc. These are processed generally in parallel in the system. And the idea is that there's going to be a location in space that if you sum across every single pixel is going to be the most visually salient location. And so in this image, the butterfly image, that hotspot is that most salient location. In this image, you can see the hotspots vary, the eyes, there's the center of the mouth where the teeth probably are, and parts of the hair. The hair is probably because it's in contrast with, with that white background, so the idea of contrast is really important in these salience maps. These are bottom-up guidance, as opposed to top-down guidance, is not meant to be guiding, orienting throughout. You know, once I look around this room, I may identify someone with a bright orange shirt, and that's going to guide my first couple of fixations. Not to That's going to guide my first couple of fixations. But then, of course, top-down processes and priors are going to come into play. I don't want to take anything away from that. I'm just showing you here what we've done with this bottom-up guidance mechanism. So here's how we've asked questions about the development of this mechanism early in postnatal life in the service of understanding visual search and visual attention. We asked basically in this study whether salient faces guide orienting in clutter more than non-salient faces. So the image here is an example of a salient face display. So you see this is a natural scene. This is a picture of my former lab manager, Sarah Haas. Her face happens to correspond to the most salient location in this display. What we did was we showed a large, over 218 person sample, 61 of whom were infants, 4 months to 12 months of age, examples of displays where either the face was salient or it was non-salient. So the idea is that the category of stimuli is the same, where we're going to measure whether or not they attended. It's the faces in this case. The clutter was made to be similar. So any more orienting to salient faces in the first few fixations of scene viewing here can be taken as indication that this bottom-up orienting mechanism is at play, okay? So let me show you briefly the full data. The y-axis here is the proportion of attended faces in the first several fixations of scene viewing. The x-axis here is age in years. Babies are over here. I'm showing you this because the data are pretty solid that bottom-up salient stimuli of the same class guide orienting proportionally more than non-salient stimuli of that class. That is, the visual environment is a pretty critical variable in getting you to a location in space. As we've known for some time, what we didn't really know is that this is not a variable that's critical in infancy, and it's not quite robust until after the first postnatal year. This came as a bit of a surprise, to be frank, because there has been an assumption in the literature that because they have so few top-down priors, that it must be the bottom-up visual system that's guiding attention orienting in infants, that's guiding the typical development of what's picked up. I was actually excited that we were able to ask in this particular study what might be the reason that this is showing this developmental change over the first postnatal year, really not robust until afterwards. And it turns out, without getting into too much detail, that this is not an efficient strategy for babies because the visual system is undergoing rapid change. So their color channel use, their orientation, their intensity, etc., we're all changing dramatically in the service of getting them to a bottom-up location, which is not one that's strategically the same even, the same scene one day to the next. So this bottom-up guidance itself is a developmental process in the service of this visual search task. We also have done this with children with ASDs. So we found that this bottom-up guidance is actually overused in children with ASDs in the 2 to 5 year range relative to age and sex match controlled children. The broader literature shows that this population has atypical visual attention profiles. This is why we asked this question. And that this may be linked to enhanced perceptual processing at the level of visual cortex. So we found that reliance on bottom-up guidance is higher, and we're now actually looking at this using head-mounted eye tracking real-world search. And I kind of want to show you here. The hotspot is just the world. Again, it's what's salient in the environment. This is the child navigating that space, and I want you to watch how their eye track, that crosshair, follows that salience map. That in fact, what looks like a really random pattern of navigating an environment in an ASD child, actually when you fit it to a model of bottom-up guidance, doesn't look completely random, which we think is really an exciting avenue. In fact, in the first study that we did, we found that the extent of bottom-up reliance in the way that I just showed you has correlates with language outcomes and social symptom severity in this group. So this is, I hope, the preliminary first in many years of investigation. But really, I'm using it here to highlight how important it is to garner precision in the attention-orienting mechanisms that are contributing to visual attention functions, both typically and atypically. Now let me switch gears here and come back to this idea of inhibition of return. So now you've gotten to a location in space, and there's going to be some mechanism that is involved in maintaining an efficient sequence of eye movements through the suppression of return of the eye movement to the previously attended location. And like I said, this mechanism is important for maximizing search efficiency so that you're not perseverative and continually repeating same eye movements. And we have some evidence here from infants and also some imaging in adults that in doing that, this mechanism is playing a critical role in sort of creating a more robust visual representation for downstream processing and encoding. Okay? These inhibition of return mechanisms have been studied using spatial cueing tests for very many years. And we make use of them to test the prediction that I just highlighted for you here. The idea is that a cue is presented very briefly. This is an overt paradigm in our case. Some period of time takes place, some delay, and then the target is presented in either the cued location or actually in the non-cued location. And the circles here are representing how we get eye tracking data. So this circle represents a fixation and then an eye movement to the right or the left. This is not what babies see. So when the delay between the cue and target is brief, there's an enhancement elicited by the cue, and targets appearing at that location get an attentional boost, and that's measured by the speed of the eye movement towards that location. So the covert orienting cue comes on, the attention is shifted towards that location, and when the target comes up, eye movement goes there really quickly. It's already being processed. When the delay is longer, nothing happens at that cued location. That location becomes suppressed, and the attentional bias now shifts to the non-cued location, and now that location is faster. Okay? What's the scenario I'm setting up for you here with these beautiful, really sophisticated arrows is that when targets are presented at the non-cued location with this long delay, when you present items at that location, they're encoded in the presence of that distractor suppression, which is not the case when you're dealing with just the target enhancement orienting mechanism. So what we did was actually really simple. We just started placing variable objects in those locations. And we asked in an unannounced subsequent recognition memory test later, is memory better, either within or between, we've done this both within and between subjects, I'll show you, when items are encoded in the presence of that now distractor suppression of the previously attended location, in this case as a function of the cue having enhanced that location. So actually kind of a simple idea. It's just putting objects in there rather than just the same target over and over again, and then testing whether memory is supported by that, in the service of understanding whether these processes are critical in linking visual attention and memory, and therefore making visual attention such a profoundly important mechanism. I'll show you very briefly support for the idea that this is enhancing both striate and extra striate representations, and I'll show you that when we've compared encoding in under inhibition of return conditions, and facilitation conditions in the task that I just showed you, in adults, we find a lot of activation. One of the few activations is in inferotemporal cortex, a region that has considered really important for visual object recognition. So there's a lot in this imaging study, and I'm happy to talk about it offline. I just wanted to sort of highlight for you that we've actually examined the mechanism that we're citing, that it's important because visual attention is modulating striate and extrastriate activity. And in fact, in the adult work, as well as the infant work that I'll show you in a moment, we find that memory is significantly better. Recognition memory for items encoded in the presence of distractor suppression is substantially better than when a simple orienting mechanism is engaged. And this is better from the perspective of baseline. We've tested these items, we have a baseline idea what the memory looks like. We've run the facilitation condition. This is a really robust effect. You will remember better when that simple difference is that delay is longer in that inhibition of return condition. So the mechanism guiding the eye movement has a pretty critical role in memory formation. I myself can sort of rest on the shoulders of giants. John Richards has done such amazing work in tracking the development of inhibition of return, and I can use that information to focus on a population to test the memory question. So there's like a button here that I just cannot identify. So he's shown that while simple orienting is in place as early as 3 months, that's actually here. The idea here is that this, the cue is the valid cue, and the cueing facilitation is much faster than the invalid cue. Inhibition of return, which is just an easy way of me saying selection via suppression process, is not solid, or in fact is variable at 3 months, but becomes much more significant as a tool by 5 months. So baby people love weeks, but I translated that because it's hard to do that on the fly. So he's also paired this with pre-saccadic ERPs that show more cortical involvement of both parietal and frontal sites with this behavioral change. So really this inhibition of return mechanism is, in his view and in mine as well, taxing the development of sort of these occipital-parietal interactions and then involving frontal cortex as well. So since the developmental trajectory is laid out here, we focus our questions about memory on whether or not on population that's 9 months of age, because we know they have a solid inhibition of return effect. We wanted to start there and lay that foundation. So the task is much like what I just showed you in adults. It's an eye tracking task: cue, delay, target, target. And then what we do is, after infants go through about 56 trials of different targets being presented during the cueing task, what we do is we give them either one of both familiar items in this case, one that was presented in the cued location, one that was presented in the critical non-cued location. I know the terminology gets confusing. Non-cued good. And then one novel test item. And the idea is that in infants, you can index memory by looking at duration of looking at novel relative to familiar things. So they love novelty, and so when you present them with a familiar item, they're now done with it, and they will have a much longer looking time at novel stimuli. You can compare that and get an index of whether or not they remembered or learned something. And so what we found now across 3 different studies is that this suppression of previously attended location, this IOR mechanism, at item encoding results in relatively better memory at test at 9 months. So this is within subject. So this is the study example that I showed you a minute ago, where the same babies are seeing targets presented in the cued location, the non-cued location, the good one, and then relative to novel. And you can see that the duration of looking at tests is higher to the novel item relative to the non-cued item. That is, they recognize this, they're less interested in it, but even the same babies, not to this cued item. The cued item is treated like it's new, but not the item that was presented in this non-cued location. which is phenomenal because the only difference is where it's presented on the screen. We've done this between subject. We thought maybe there's something about the within subject effect, and we get something very similar, briefly. This is the novel compared to the familiar item in IOR. This is the novel compared to the familiar item doing nothing in the facilitation, the simple orienting condition. And there's no difference in baseline. And actually, briefly, I'll tell you that we've actually done this with, we've tried to reverse there's a perceptual narrowing effect in infancy that happens right around 9 months. That's called the other race effect, where babies at 3 months can distinguish between their own and other race spaces, but by 9 months, they no longer can discriminate between other race spaces. This happens for sound stimuli of native and non-native tongues. It's phenomenal because it gives you an opportunity to really study what is happening in these types of effects. One hypothesis on the table is that this is an attentional bias type of an effect, that given the exposure and experience they have with own race spaces, they kind of garner special attentional selection. That category becomes attentionally selected in a slightly different way. So this is a great paradigm to experimentally test that because we can bias attention to a set of stimuli or not. And we find that when you take a group of Caucasian 9-month-olds and you present other race spaces, they often have trouble. And then if you present them in that non-cued location where you're getting this distractor suppression, they now can tell the difference, and only in the non-cued case, only if they're presented in that non-cued condition, between the familiar and novel other race spaces. So it really is having an effect on how information is being learned, and we find that sort of exciting. So just to briefly sum up this last part before I do the last 2 minutes. Do I have 2 minutes? No. So again, this inhibition of return mechanism is showing developmental change, and it's important for memory formation and learning during the visual search process. What that means is that in those between 3 and 5 months, when you're not getting this mechanism at play, learning is literally different in that population than when this mechanism comes online and is supporting visual search processing. What it also means is that populations who have disruptions in inhibition of return beginning early in postnatal life and also extending throughout, I know IOR has been shown to be disrupted in schizophrenia, ADHD, Parkinson's, etc. This might be an interesting way to think about how early the developmental trajectories might be at least behaviorally considered. This isn't work from my lab, but very briefly, Katie Thomas and Julie Marquand, who did all the work on the inhibition of return mechanism, have shown that, we know that they've shown that COMT, that variations in dopamine signaling, likely in prefrontal cortex ARD, contribute to individual differences in inhibition of return in infancy. That is, they found that COMT val carriers showed robust IOR relative to infants with the MET-MET genotype. So this is just a little bit more information, sort of heeding the call of Dr. Jernigan the other day to think about different ways of asking questions in our populations that bring in behavior and genetics, etc. In my lab, we've gone after socioeconomic status, given the importance of this mechanism, and given what we know about genetics. Is socioeconomic status a variable that's of interest when thinking about the development of this mechanism? And actually, we show no relationship between socioeconomic status and this mechanism and the development of this mechanism. However, and this is the last point I'll show you, we do find that infant socioeconomic status correlates with their memory performance on the recognition memory task. But that's only in this when items are encoded in the facilitation or baseline condition, in that simple orienting condition. So SES here is predicting memory scores. However, when we engage this inhibition of return mechanism in this condition, SES no longer has a predictive effect, suggesting that, you know, these individual differences in memory, even within the populations that we're dealing with, might be protected by engaging attention mechanisms that orienting that are meant to sort of engage a robust signal at encoding. So, in sum, attention and memory are deeply intertwined, shedding some light on why attentional performance in infancy seems to shape outcomes in other domains. Both bottom-up guidance and IOR development support change in visual search skill in infancy, and these findings, I hope, lay the groundwork for some precision investigations of downstream effects of attention across the lifespan. So, with that, I will show you my mouse at P4. He's so cute, I can't believe that just happened. At P4, at P30, at P90, and I'll say thank you.
take one brief question.
Please go ahead. Oh.
Mine is just a statement. Great talk, and I just really want everyone to perceive how important it is to have these different approaches in the sense of going really early into infancy and the potential, the predictive potential that this has going forward, but using these computational models that really can link us to the brain in other ways. So I just wanted everyone to keep that in mind. Thank you.
Thank you guys so much.
Thank you. Can I get Alice to come up, please? In the meantime, yeah, we can take another question. Brad and Alice, if you're here. There you are. Okay, great. So you can go ahead and answer.
So, Brad Schrager from Washington. I'm really interested in the idea of these early measures and predicting the ultimate behavioral outcome. So, for example, at 3 months, you looked at pop-out and effort flow. To what extent did, in a given individual, did pop-out behavior correlate with effort flow? And then, to what extent do those features predict IOR behavior in a given individual down the road? How much variability?
Pop-out and effortful search do different with the IOR than the pop-out searches. The pop-out search seems to be more important for a much more rapid getting to that location, whereas the more effortful search tends to involve going from one place to another, literally in that sort of classic, not here, not here, not here, not here, and that tends to be more related to the ability, getting to the right location, the target location, given they have no idea what the target location is. These are 3 months, right? Tends to be more related to the ability to sequence those eye movements in an efficient fashion.
Thank you. Okay, next up we have Alice Graham from Oregon Health and Science University.